Right. Is this working? I think so. So let's see. Or maybe it's not. What is Google saying? No, it's working. Okay. It's saying no data for a moment. Alright, this is day 14 for the Admin Code Challenge. Yesterday's kicked my butt. So the second part of this problem turned out to be quite a doozy. Well, I guess it would have been easy if I knew the basic underlying concepts here. I did eventually have to get some help on this one. The key point here was that we had a series of primes. So all these numbers are primes. That's one key feature of our data input. Technically, it could have been solved without primes, but the prime thing was a big hint. So there's this thing called linear congruency, linear congruent expressions or equations. It basically is something that looks like this. Where did that go? Yeah, right here. So you have sort of an expression here that kind of says that you have a function of integers, greater than 1, and this congruency kind of like says, if your list of integers kind of follows this, if it's a moduli of 17, there's at least a remainder of 0, at least once. And if you kind of combine these into multiple ones, what's called a sequence of linear congruencies, there's this rule called the Chinese remainder theorem. And basically what it says is that if you have a list of congruencies like this that are all coprimes, then there exists one linear congruency that's true for all of these. And the trick here that turns out to make our solution fast is that once you've figure out the congruency for, a set of 2, set of 3, then that congruency that you find out is true. You can kind of like compound your answer. You can use it to figure out the next one and use that to figure out the next one. So like here, this was one of our examples. It was, you have a timestamp that's divisible by 17. You have a timestamp that's position 2 that's divisible by 13. You have a timestamp of 19 at position 3 that's divisible by 19. And what we were doing before is checking every single number. Well, every single division of 17. We would go to 17, check if, position 2 is divisible by 13. Then check position 3 divisible by 19. And the problem was that was super slow. I'm gonna need to jump into 14. But yeah, basically I needed to apply that theorem, which turned out to be like, you start with the first lowest common multiple or divisor. No, lowest common multiple, yeah. And then once you've found a number that satisfies that lowest common multiple, then you can take that, multiply it by the next common multiple, and just keep doing that and that instead of checking every single number. And it reduces the search space greatly. Alright, your ferry approaches the seaport. The captain asks for your help again. Let's see. Brief inspection, you discover the seaport's computer system uses a strange bitmask system. The initialization program, your input, can either update the bitmask or write a value to memory. Values in memory addresses are both 36-bit unsigned integers. 36-bit unsigned integers. Okay, that's weird. For example, ignoring bitmask for a moment, a line like mem8 equals 11 would write the value 11 to memory address 8. A line like mem8 equals 11 would write the value 11 to memory address 8. Okay, and each memory address is a 36-bit unsigned integer. So technically a list of those integers. The bitmask is always given as a string of 36 bits, written with the most significant bit representing 2 to the 35th power on the left, and the least significant bit to the power of 0, that is, on the right. Isn't that how it normally is? The current bitmask is applied to values. No, I think it's opposite on integers. No. On the right. Okay, I'll have to think about that when I get to it. Current bitmask is applied to values immediately before they are written to memory. A 0 or 1 overwrites the corresponding bit in the value, while X leaves the bit in the value unchanged. For example, 0, 1 overwrites the corresponding bit in the value. So we're going right to left. Specifies a bit mask. The mask it specifies will overwrite 2 bits in every written value. The 2's bit is overwritten with 0, and the 64's bit is overwritten with 1. Program then attempts to write the value 11 to memory address 8. I'm a little confused here. The initialization program can either update the bitmask or write the value to memory. Values and memory addresses are both 36-bit unsigned integers. A line like mem8 equals 11. Oh, this is the command. Is that what you're telling me? Would write the value 11 to memory address 8. Will overwrite 2 bits in every written value. The 2's bit is overwritten with 0, and the 64's bit is overwritten with 1. You specify a bit mask, which is this guy. Oh, I see. 0, 1 overrides the corresponding bit in the value. Well, X leaves the bit value unchanged. So we need to apply this mask to this value before it's written. Overrides the corresponding bit in the value. The 64's bit. 2, 4, 6, 8, 16, 32, 64. The program then attempts to write the value 11 to memory address 8 by expanding everything out to individual bits. The mask is applied as follows. Okay, so 0, 1 is overwritten as 0, and this is overwritten as 1. This stays as 1, this stays as 0. Okay. Execute the initialization program. What is the sum of all values left after it completes? So let's start. Let's see what the puzzle input looks like. Okay, so we're updating the mask for the following commands. I see. So let's try this guy first. All right, so how do we want to do this? So this mask can apparently change as we're going through the program. How do we know how big our memory is going to be? Does it tell us? Values and memory addresses are both 36-bit unsigned integers. Okay, so my memory can be up to 36, whatever 36 bits is. Ooh, can I even allocate something like that? I guess I can use a long and just ignore the bits that aren't within 36. What do I say? Memory. And the length is going to be max int, I guess we'll call this. So it'll be 2 to the power of 36. What are you complaining about? Yeah, it's more than we can support. But what did our input show? We don't have any numbers that... Wait, what did we say max int was? This huge number. But in our input, doesn't look like we're going past 16 bits. 16 bits being what? 65,000 or whatever. Doesn't tell us how big our memory is. I'm spending too much time on that. So let's say long memory equals 16 max. I guess I have enough memory for that. All right, so how do we assign the mask to a memory location? Well, I guess we don't. We just need to work through this one at a time, right? What is the sum of all values left in memory after it completes? You know what? Let's just use a list. No, I can't do that. I guess we'll just parse it as we work through it. So what do we want? Read all lines is a list integer string array. Now, all right, for each line in lines, if line, if it starts with mask, then let's see, let's call current mask let's just call it a long. Have it set as 0. If we're on mask, we'll grab it with regex.match line. We're gonna match mask equals, and then yeah, pretty much anything. Groups 1. How are we going to do this? Let's reverse it. No, we can't. I want to turn this into a mask. So how do we use a mask? The X's is confusing. I mean, normally you could just do a bitwise AND or a bitwise OR, but with the fact that we have a 0 or 1 in weird places, makes it a little bit more difficult. Let's reverse this so we don't have to worry about the is reverse a void? No. I don't want to have to loop through the mask. What do we do here? A 0 or 1 overwrites a corresponding bit. Actually, it's a 0 or 1. Maybe I can have it as 2 masks? Or maybe 3 masks? Because I guess you can first... So let's say it was... The value was a 1, and our mask was nothing. If we... How do we leave it unchanged by applying something twice? Yes. We'll do a double, two masks. So first, so what do we want to do? If we apply 1 twice, all right, if we apply a 1 and then a 0, we'll return it to whatever it originally was. So I dot now we want how do we change a single bit? We need to bit shift, right? So we would say current mask. Oh, it's getting complicated. How do we do a bit shift in PowerShell? So if we start at one, okay. Current mask. One shift I. All right. Oh, we need to check. So if mask I equals X, then shift first mask will shift once. What did we say we wanted to apply a 1 and a 0? One, 0, 1, 0. Okay, a 1 and a 0 to leave it unchanged. So let's say if we had a mask that had the 1-bit set, zero, shift left once, we should have this flipped to 0, right? No. Okay. I guess you don't have to set it to 0 for the second one. It's already 0. Oh no, wait, we do, because just in case, because we're overriding the old one. If the mask equals 1, so for 1, what did we want to do? Um, uh-oh. Oh, I'm not doing this right. Should be 1 twice. We wanted to set this to 1. Dang. I guess we don't need to do this at all. We just can just bit shift every time, right? Uh, okay. So if we come across current mass, if we come across a 1, we'll just bit shift 1 into the this guy. Let's create a function up here called apply mask. So that equals val and bit shift a 1 into the I position. Else Otherwise, we're going to bit shift a 0 into the I position. Oh, sure. All right. We want to get memory. Mem. Mem at position. Oh, we need to get mem position equals let's see, let's grab out the memory position. We're gonna say mem and in here it's gonna be our memory position. And here it's gonna be our value. So memory position equals parse the capture 1 and value is going to be capture 2. So memory at mem position equals apply mask, current mask, and val. Use of unassigned. How about that? Okay, hasn't thrown any errors. So what do we want to see? What is the sum of all values? In the above example, only two values in memory are not 0. 101 and 64, producing the sum of 165. So all the values of none that aren't equal to 0 give me the sum. What do you get? 0? Let's see, our mask is this. Right, position 0, we reversed it. Decimal 101. Yeah, that makes sense. All right. So memory position 8, we're applying the mask to a value of 11. We should get 73 back. Whoops. What did we get? Position 8 equals 0. Let's debug that again. All right, the first one is at X. The second one should change position 1 to 0. All right, so what is our value now? 0? 11. Hmm. What would be 11 in bits? 1, 1. What would it be 11? 8, 9, 10, 11. So 1, 1, 1, right? 1 plus 2. No. 1 plus 2 plus 4 is 7. 1, 1, 0, 1. 3 plus 8 is 11, right? So after we apply the first bit mask, it should change it to this. We're changing position 1 to 0. I want to see. Hmm. This value changed to 0. Oh. That's because I'm wiping it with end. Oh, here we go. What do we get? 165? Okay. So let's get our puzzle input. And it took a while to kind of figure out, but oh well. Index was outside of the range. Mem position 33,000. What's the max value of int 32, int 16? 32,000? Really? I thought it was... Oh. Uint 16 is 65,000. Oop. Let's not do that. Oh, that's a giant number. Okay. What is the sum of all values left in the memory? It's not the right answer. But we got the right answer for this one. What's special about this that's giving us bad answers? The long should be big enough. Is there anything special about this mask being applied? Initialization program can either update the bit mask or write a value to memory. I wonder if we're doing some sort of overflow here. To the power of 36 gives us a big number. When we ran our program, we got a value that was larger than 36 bits. Let's see. Now, what are we doing when we're setting the value twice? This time this time the mask has no effect. Finally, the program tries to write 0 in address 8. Value 64 is written to address 8, instead of overwriting the value that was there previously. Okay, so we don't do any looking at the old value. Let's see if let's see if any are going to show up as larger than our max integer value. No? Didn't have any. Well, I guess it never would, right? Because we're only applying values to 36 bits. This is sum of all values left in the memory after it completes. Input looks okay. Bitwise OR operator used on the signed extended operand. Consider casting to a smaller unsigned type first. Maybe set these to ulongs? Does that matter? Cannot be applied to operator of type ulong and int. Where is the signed bit? Is that the last one? Hmm. Oh. Why are you so big? Let's see. Most significant bit on the left and least significant bit on the right. So it's unsigned if 2 to the power of 35 is on the left. Let's see. 36-bit unsigned integer. Sum all the values left in memory. Why? Why wouldn't you be right? Not really doing anything super complicated here. Oh, I guess this is a problem too. Setting it to 0 might not be right. Okay, yeah. We weren't setting that the 0 bit correctly. Let's see. For some reason, the C port's computer system still can't communicate with your Fairy docking program. It must be using version 2 of the decoder chip. Version 2 doesn't modify the values being written at all. Instead, it acts as a memory address decoder immediately before a value is written to memory. Each bit in the bit mask modifies the corresponding bit of the destination memory address in the following way. The bit mask is 0, the corresponding memory address is unchanged. The bit mask is 1, corresponding memory bit is overwritten with 1. The bit mask is X, the corresponding memory address is floating. What? In practice, this means the floating bits will take on all possible values, potentially causing many memory addresses to be written all at once. When this program goes to write to memory address 42, it applies the bit mask. After applying the mask, 4 bits are overwritten, 3 of which are different, and 2 of which are floating. Floating bits take on every possible combination of values. Okay. Next, the program is about to write to memory address 26 with a different bit mask. Okay, what do you do with these 8 things? The entire 36-bit address space still begins 0. You'll need to sum up all the values left in memory. This is 208. All right, so we got a weird memory. So let's change our memory storage to a dictionary. Position, and let's give it a U-long value. Well, we'll give it an array of U-long values. Oh, let's not use the U-long either. Long should be fine. Because the sign is at the very end. Let's call this new mem. All right, so we're going to do something similar. So we're going to grab the mask, grab the memory, but this time we're going to use a long, but we're going to create another apply mask function. And this is going to give us back an array of longs. All right. We're going to populate a list of values, first with value 1. Now our rules were if the bit is 0, it's unchanged. So if we're 0, we continue. If the bit is 1, it's overwritten with 1. So we're going to say for each value in our list of values, we are going to set its one value to 1. Can it assign in value because it's for each iteration? All right. Otherwise, if we get an X, we need to create we need to do this. We need to replace the list with a new one. We're going to go through our temporary values. And we're going to do two things. We're going to set, it's going to be either 0 or 1. The first one's going to set it to 0. Okay, so every time we come across an X, we'll add 2 new values to our list. And then new vals will equal temp vals. Let's call this apply mass too. Can I convert from long to U long? Where are you? Oh. What are we doing? And then we're going to say new memory. Select value, select many. And then sum. Can we do that? We can. So let's do our test memory again. Or no. Did they change the test input? Yeah. What do we want? 454? That's not right. All right, our first set. Can we... Let's reverse this so it matches up. And then add left. Add it with what, zeros? You got to be difficult, don't you? What? Why are you an enumerable? Oh well. We'll just have to know that it's reversed. So we get 4 values. Nope. This isn't right. Well, this last bit should have been a 0 or a 1. But instead we got 2 1s. Ones and zeros. No, that's the first bit that we're looking at. Oh, none of these look right. What are the rules again? The bit is 0, the memory address is unchanged. The bit mask is 1, memory bit is overwritten with 1. this a problem? Ooh, that might have been it. 0101, 2 zeros. No, but this one should have been. First bit didn't get changed properly. Wait, value 100. Oh, what are we doing? Doesn't modify the values being written at all. Memory address decoder modifies the corresponding bit of the address of the destination memory address. Ah, I see. So we need to get for each memory address in this memory position. And we need to change this to change this to long too. So down here, oh. Took decimal 42, and it should be $59, $27, $58, $26. Okay. Oops. That gives us 208. Is that correct? It is. Let's get our puzzle input. Again, let's get rid of the prints. Ooh, whoops. Okay. We get this big number. There we go. We got it. Not too bad. Yeah, I didn't do very good on the part 1, but not too bad in part 2. I cracked 3,000. Yeah, this one was kind of tricky. I guess the first part was the thing that really wasted a lot of time was this guy resetting the bit value for a certain position to 0. And I guess also trying to figure out how I was going to go about doing this. The bit shift thing was the answer. I was thinking of creating 2 masks and then applying it twice, but that wasn't really the answer. Basically, what we're doing is they're giving us a backward mask or a backward number. Usually numbers are stored, like left to right. So if you have a number that's, a value of 2, it would look something like this. 0 being the 1 bit, 2 being, this one being the 2 bit. So we set 2, and this equals a decimal of 2. If we had a mask of this, x1, xx, or x0, xx, it's basically telling us that, hey, we need to shift this bit right here. So we can just do something like this. Bitwise or, and then say, let's actually say this. Let's show the 1 first. So we'd say this, or 1 shift position 0. And this would be equal to 3. Yeah, reversing it saves a lot of time. You don't really have to worry about the 36-bit thing. I mean, as long as it fits within, whatever data type you're using, the rest of it's going to be all zeros. So if this guy was, a 32-bit integer, it'd be, whatever 32 zeros would be. So this guy, we stored it in a, integer, it would still equal 2. If we tried to do it backwards, then this would actually be, something like whatever that 2 to the power of 31 is. But anyway, yeah, that's it. This one wasn't so bad. All right, that's it for this one.